This video is going to walk us through how to simplify radical expressions. So radical is the opposite of an exponent. We're going to look at two types of radicals, square roots and cubed roots. And you can tell the difference by the index. In a square root, you won't see the index there. It's going to be implied. So we would never, for example, see this, but we will, however, see things that look like this, which means that we're looking for the cubed root. Okay. So how to simplify a radical? For all of these problems, whether it's a square root problem or a cubed root problem, we are going to create a factor tree. So what that means is that underneath 24, or whatever number is underneath my radical, I am going to try to think of two numbers that multiply to be 24. It could be 6 and 4. It could be 8 and 3. It could be 12 and 2. The nice part about simplifying radicals is that any of these will work. So you could have a different factor tree than your peer. You guys are still going to end up with the same answer at the end of the problem. Okay? If you're having trouble with your multiplication tables and you just cannot figure out what multiplies to be 24, then in your calculator, instead of attempting to guess and check every single time, use division. So 24 divided by 2 would give you 12. So then you know it's 12 and 2. Or 24 divided by 3 would give you 8. So then you know that the factors are 3 and 8. So use division to your advantage, especially when the numbers are a little bit bigger and you might not know what multiplies to be that value off the top of your head. All right, so I'm going to use 3 and 8. So 24 underneath, I can write 3 times 8 is 24. Those are two factors that I'm branching out in what is called a factor tree. Then I keep going, and I want to come down to only numbers that are prime numbers that I can't multiply two things to get that answer. So 3 is done, but 8 is 4 times 2. And then I can break the 4 down to be 2 times 2. So at the end of the problem, I end up with 4 different factors: a 3, a 2, a 2, and a 2. Okay? The 4, because I broke it down, that's not one of my final factors in this problem. And same with the 8. So if you want, you could cross out the 4 and the 8 after you break it down in the 24. You can also check yourself if you multiply the 4 numbers that you have left, or however many numbers. So if I multiply 3 times 2 times 2 times 2, that would give me an answer of 24. So then I know that I have all the correct factors. So for step 2, either couples or triples are going to go out and singles will stay in. The couples or triples is dependent on whether or not you're finding a square root, which would be couples, or a cubed root, which would be triples. In this case, I'm finding the square root of 24 and simplifying that. So I am looking for couples. Couples will go outside of my square root and singles stay in. Okay, so I have a pair of 2s. And then I have a single 2 and I have a single 3. And you can pair off any of the 2s. As long as you know if you have 3 of them, you would have 1 pair of 2s. Okay, so the couples go out, which would be in front, and the singles will stay in. Now, for step 3, if you have multiple couples, triples, or singles, so anything, if there's a multiple, you always, always, always will multiply them together. So because I have a single 3 and a single 2, I'm going to multiply those together, which will give me 6. And this would be my final answer. That would be the simplified number for square root of 24. If the radical has a coefficient for step 4, we'll look at that example in a minute. If it has a number that is outside of the radical already, you will multiply it by whatever couples or triples you put in front. Okay, and then is this answer rational or irrational? Because this is not a perfect square, the answer would be irrational. For example 2, we are going to find the square root of -3 root 256. So this one does have a coefficient in the front, which we'll talk about at the end of the problem. When you start the problem, you are just creating a factor tree for 256, just for the number that is underneath the root. Now, this problem is going to look a little bit different because 256 is actually a perfect square, which some of you might already know that off the top of your head, and then you can jump to the answer. This is also a bigger number, so you're not going to know necessarily off the top of your head what two numbers multiply to be 256, unless you knew it was a perfect square. Now it is an even number, so you could divide by 2. If you continue to just divide by 2 over and over and over, your factor tree is just going to be a really big factor tree, which is fine. It just might take you a little bit longer. So I'm going to divide this by 4, and when I divide by 4, I get 64. So that means 4 times 64 is equal to 256. Okay, then the 4 breaks down into 2 and 2, so that would be a pair. And then what I could do is for 64, hopefully we know that that is 8 times 8. If you don't, you can divide it by 2. That's 32. Divide 32 by 2. You get 16. Divide 16 by 2, and so on and keep going. But if you can come up with a pair earlier on in the problem, then I can go ahead and circle this as a couple, and I do not have to keep breaking it down. Now, you can break it down into 4 and 2 and 4 and 2 and then 2 and 2 and 2 and 2, and you would just end up with several different couples, which again is fine. It doesn't matter which way you approach the problem. Regardless of how you did this one, when you get to the end, you should have ended up with no singles, only couples. So if you have a scenario where you only have couples, that means that you don't have a square root. You only have numbers that are going in front of the radical, which means that your answer is just going to be an integer. Okay, so I would take 8, which is a couple, 2, which is a couple, and multiply those together. And then you also multiply it by the number that's already in front of the radical. So multiply that by -3. And that would give me -48. So is your answer rational or irrational? This would be rational. So before I move on to example 3, I want to talk real quick about just checking our work. When you type, so for example 1, if you type the square root of 24 into your Desmos calculator, the scientific calculator, it is going to just give you a non-terminating, non-repeating decimal. It was an irrational number. But if you type in 2 square root of 6, which is what we got for our answer, both of these decimals should be the same if you did the problem correctly, because you found the radical, you found the other radical, they should be equal to each other. So for example 2, if you typed in -3 square root 256, because this is an integer answer, you should have actually just gotten -48 with the calculator. So that will help you to know that it's a perfect square and that when you do your factor tree, you should not have any singles. For examples 3 and 4, we're going to approach these the exact same way. You still create a factor tree even if it's a problem with a cubed root. The difference will come at the end of the problem. Instead of looking for couples, we're going to look for triples. Okay, we want sets of 3 numbers versus just pairs. So for 72, I'm going to break it down into 2 times 36. And then what some people are going to do is, okay, well, that's great. This is 6 times 6, and then I can circle those. Again, I'm looking for triples on this problem. So that helps breaking it down into 6 and 6, but I can't stop there and circle those because I don't have a third 6. Now, if I had a third 6, then you could stop and go ahead and circle your triples, but I would need to keep going. So 6 would be 3 and 2 and 3 and 2. So then now I have 3 2s, and that would be my triple. And then I end up with a single 3 and a single 2. I said that wrong. A single 3 and a single 3. Okay, so for my final answer, I would have the cubed root. Triples are going to go outside of the house, similar to couples going out. So I have a set of 3 2s that will go outside of the root. Make sure that when you are writing the cubed root that this 3 is small and it doesn't look like a coefficient. It doesn't look like it goes in front of the radical. Okay, it should just be a small 3. And then my singles go inside the house. Now I had 2 singles, a 3 and another 3. Whenever you have more than one, you multiply them together. So that would be 9. So my final answer would be 2 cubed root of 9. And this would be irrational because it's not a perfect square. Example 4, we're breaking down 250, which can be a little bit of an intimidating number because it's such a big number. But if you ever have anything that ends in a 0, that automatically means it's divisible by 10. So this would be 10 times 25. Then 10 is 5 times 2, and 25 is 5 times 5. So at the end of my problem, you have a 5, a 2, a 5, and a 5. And as a reminder, I said this in the last example, but in example 2, if you multiply all of your final factors together, so 5 times 2 times 5 times 5, you should get 250 if you did your factor tree correctly. Okay, so I have 3 5s, and then I have a single 2. So for my cubed root, the 3 5s would come out front, but we have to be careful because there was already a 5 in front of the radical at the beginning of the problem. So whenever you have a number that is already in front, you multiply it by whatever couples or triples you're bringing out. So since I had 3 5s and I'm going to put that in front, times the 5 that's already there, that would give me 25. And then the single 2 would go inside. So this would also be irrational. So for example 5 and 6, we're going to look at simplifying radicals that also have variables. So we're going to approach these the same way. We're either going to look for couples or triples, depending on if it's a square root or a cubed root problem. And for the variables, we're going to do the same thing. Just look for pairs of variables or triples of the variables. And I'll show you that at the end. So to start the problem, you're still going to break down the number underneath the radical the same way by using a factor tree. So 128 would be 2 times 64. And then for 64, we can break this down several different ways. We could divide by 2, we could divide by 4, we could also divide by 8. I said this earlier, but if you can recognize when a number is a perfect square, especially for a square root problem, then you can find a pair and circle it and be done with your factor tree. So if I know that 64 is 8 times 8, then that's a pair and I don't have to go any further with my factor tree. If you break it down into 4 and 2, and then you break the 4 down into 2 and 2, then you would end up with 3 different couples of 2s, which when you multiply 2 times 2 times 2, you would still get 8. Okay, so I'm going to stop here. This would be a pair of 8s, so that would go in front. and then a single 2, so that would go inside. And I'm leaving some space here because we have our 3 variables that we need to work with as well. And some of those are going to be couples and end up in front. So x squared is the same thing as x times x. If I'm making a factor tree, x times x would equal x squared. So the question is, for that, how many couples, or do I have any couples? Well, if I have a pair of x's, that would be considered one couple. So outside of my square root in front, I would just put 1x because I have one pair. And that leaves me with no singles. So underneath the radical, I would not put the variable x. Then for y, I have 3 y's. And you can write it out every time. You don't necessarily have to write it out every time. If you have 3 y's, that would make one couple. So 1 y would be in front, and then you still have one single. Then for the z, if I have 10 z's, and you can write it all out or just start to divide by 2. So if you have 10 z's, that would make 5 couples. And if it helps you visually, then just write it out. 3, 4, 5, 6, 7, 8, 9, 10. So I have 1 pair, 2 pair, 3 pair, 4 pair, 5 pair. So this would be z to the 5th power and no single z's. So this would be my final answer. And just be careful with your notation. Z to the 5th, if that 5 kind of slides over and it looks like the 5th root, that would be incorrect. And especially on the next problem when I do have a cubed root, make sure that you can tell the difference between your exponents and the root that is in front of the square root. So for example 6, we're going to start by doing a factor tree for 81. So that would be 9 times 9, 3 times 3, 3 times 3. So I have 3 3's and I have a single 3. So the triples would go in front, and then the single 3 would go inside, and this is the cubed root of 3. Then for your variables, this one's going to be a little bit different because instead of looking for pairs, I'm looking for triples. So if I have 7 p's, that would give me 2 triples of p's, and then 1 single left over. So I would have 1 p underneath, and then in front I would have p squared. Then for the q, I only have 2 of them, so that doesn't even make a triple, which means they're both singles. So this would be q squared underneath the root, and this would be my final answer.